I will, maybe I'll excuse Monta and myself from not appearing on the camera today. We both have pink eye. So we'll spare you all the visual of that.
Thank you, Megan. So yesterday we went through a lot, and as I said, it might be a little bit overwhelming, but just making sure we go through this several times will get us to a point where it all starts making sense. So yesterday we stopped at Lambda Expressions, and let me share my screen here. Can you guys see?
Yes.
Great. So again, Lambda expressions are really about writing functions in an anonymous way, meaning there are situations in which you don't need to give a name to a function, and you use something called a Lambda expression. And it's pretty straightforward because we use that empty slash symbol that you see there, I've highlighted, and then we specify the parameters, in this case that x for the Lambda expression or the function, and then we have this arrow guy, and over here we have the result that the function evaluates to. So in this case, we have a function that takes in one parameter, and the parameter is x, and it returns that parameter, and it adds to it that parameter plus one. I mean, what would that look if we want to run this in our repo? So we would specify the Lambda expression into parentheses like that, and then we will pass the parameter, and in this case, being a function that takes one parameter and add one to it, if we give it 4 as a parameter, we will get 5 as a result. Here's another example here where we have a function that takes 2 parameters, that's x and y, and return the sum of those parameters. What we call this in our repo or Haskell compiler window console, with 3 and 5, we get 8, it being the sum of those parameters. So very quickly, if we want to try that here in our repo, so remember, we first need to get into the compiler, JHCI, and I write my Lambda expression in between parentheses. So that's my function that takes in one parameter. I have my arrow there, and it returns that parameter, adding 1 to it. So, and if I want to call this function passing it 4 like that, I get 5. So if we do the second case where we have a function that takes 2 parameters, in this case x and y, and return the sum as the result, and to call that function, we just add pass two parameters, in this case 3 and 5, and we get 8. So again, going back to what Lambda expressions are useful for is that sometime in the context of writing a function, you don't need to name a function. So it's not necessary to give it a specific name, you just use it on the fly. And that's where Lambda expressions are useful. When we get a little bit further with something we call higher order functions, which are simply functions that takes in other functions as parameter. At that point, we will see more examples of the use of Lambda expressions. So any questions here before we move on to recursive functions?
So basically, there's not, the only thing that is eliminated is the name when it comes to how you showed us how to construct functions earlier, and the purpose for that is so that we can use these functions on the fly.
Exactly.
Okay.
Yeah. Plus, it looks more like mathematics, and those who write Haskell love stuff like that. But it doesn't have to be that way. So next, let's talk about recursive functions. The general concept here is learning how to divide and conquer. So you have a bigger problem. You want to solve it. You know how to solve, like, let's say, a tiny portion of it. And then you generalize that tiny one-step solution to the whole problem. And I will jump straight to one example here that we all know in mathematics. We have something called GCD, which stands for the greatest common divisor. So you are given two numbers and you are trying to figure out what is their greatest common divisor. So basically, the definition in mathematics states that if we take, for example, we consider the GCD of 20 and 8. In this case, it would be 4, but how do we get there? The algorithm states that in order to figure out the result, the GCD of two numbers, you need to go step by step. The first step, you figure out the remainder of the division of the two numbers. So in this case, 20 and 8. So if that remainder is superior to 0, and then in the next step, you restart the same thing, but in this case with 8 as your first number and 4 as the second number. Let me just jump down here and it might make more sense. So here again, we start with two numbers, m and n. They are integral number. They are constrained by this class. So meaning they are either integer or int that we saw yesterday. So m, and n, my terminal condition is that if I calculate the modulo of m and n, and I get 0, and then at that point, n is the greatest common divisor for m and n that I started with. But if at my first step I calculate that and it's different than 0, which is what this otherwise is saying. So if this condition here, modulo the m and n is anything else other than 0, I fall under here. And in that case, I'm going to recall this function within its own definition, but with a smaller problem. The smaller problem being what? Being calling it with n this time, n being the second number, the second parameter here, and modulo the m and n being the rest of the division we get from by dividing n by n, if that makes sense. So here, recursive functions actually use, you see a function here that is being called within its body. So this is a concept that is really central to functional programming, as it's used to solve looping problems that we have in, in object-oriented programming. When you have this kind of problem, you can just loop. There's something called like for loop. But here in Haskell, generally when we get to this kind of problem, we need to use, recursion. So let's make sure that we get this by typing another example. So if I get here and I do, I have a function called calculate my sum. Let's say it has type. We take a list of int and then we return an int, which is the sum of all the int we have in this list. So calculate my sum. So what's going to happen? So I will say if I get an empty list, then I return 0. If I get a list that has one element and many other elements, this syntax here is basically saying that I am dealing with a list that has, I'm putting apart like the first element in the list, and this is the rest of the elements. So my step would be taking that element and adding it to, I recall the same function, but this time with XS. So what I've done here is I have a bigger problem, which is calculating the sum of elements in my list, in this case, ints. And what I do is I have my terminal case here, which is if you get to empty list, just return 0, knowing that 0 is a neutral element when it comes down to sum adding. But if you get a list that has at least one element and other elements in it, what you need to do is to add that element and call back the same function, calculate my sum, but in this case, passing it like the rest of the element in the list. So what will actually happen is when you execute this, it will get the first element, X, and then it will look at this and say, oh, this is another call to another function. And the same process will happen in here. So this call will start with this and evaluate that. And if this element here is an empty list, and then it will just replace this whole thing by 0, like that. But if this element here is not an empty list, and it's something that looks again like this, so we'll get another plus x here, something like that, plus x2, x2, I can get it right, plus, and so on. So at the end of the day, we will get the sum of all the elements. Does that make sense?
I see what you're doing there. So is x the first element in the list, and then xs represents additional elements in the list, or is x the is x the first element in the list, and then xs represents the remaining elements in the list?
Exactly.
Okay.
Yeah. So you know, and there's another notion behind this called pattern matching. So you are literally like, you know, you are literally, how can I say this? You are matching the body of the function with a given parameter. Like in this case, for example, we are saying that, you know, if this gets called with an empty list, you get that 0. So that's a pattern. And if it gets called with an element and another list, and then you get, you know, you get this. So I'm using that first element, and I'm recalling this function and passing it the rest of the list. So again, what will happen here is when the compiler looks at this, he says, oh, I need to evaluate this. But it will look at this and say, oh, it can either be this or that. So in case we have an empty list, meaning that this xs is empty, we will return 0. So in that case, we'll get x plus 0, right? But in case we get x here plus the rest of the elements that are different from empty list, meaning we have a few more, what will happen? So we will get, this will be replaced, this whole thing. So if I can just, let me make sure that this whole thing will be replaced by something like this. So this whole thing will be replaced by, let's say x2, x1, plus, you know, in order to calculate sum of the remaining list. In this case, let's say xss. So what will happen here, you know, this guy will be decomposed in its first element and the rest of the elements. So the first element would be this x1 here, and the rest of the element will be this one over here. So we'll do that until it gets to the terminal case, which is this. Yeah, and at that point, Haskell will sum all this value, x plus x1 plus x2 plus x and so on, until it gets to 0. So that's a recursive function, which is a very neat way to solve like problems, but it's also really hard to, I mean, it reads very well, but sometimes it can get a little bit, can be harder to get your head around it.
Okay, that's helpful.
Okay. So now if we want to try this in the REPL, give me 1 second. I'm having some issues with my REPL here. Okay, HCI to get into my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to go to my REPL. Okay, so I'm going to And I will do this ls to see all the files that I have. So we just wrote that function in this file main.hs, that right there. So I will load it up into my repo. And we get some problems here. So pretty much expect the type actual int function is applied to one argument. Okay, there you go. So my type right there is wrong because I specify what I get as an input, but I didn't specify the result. So that's int. So I get a list of integer and I return a list. Now an int. I get a list of int and I return an int value. So I will go back to my repo here and reload. Now everything compiles and it's happy. So let me just make sure create some space there. So if I call this function, if I call calculate my sum and I give it an empty list, I'm expecting 0 because that would be this case, right? So do that, I get 0. If I call this function with one value in my list, I expect that value. But if I get to 2 values, I expect the sum of those 2 values, and so on. So that's all about recursive function. So in general, you know, with recursive function, you recall the function within its body with a smaller problem, making sure at each step you are, you know, taking your problem space and you are reducing it in a smaller problem, if that makes sense. And now you have like a terminal case because, you know, if you are calling a function within itself and you don't have a terminal case, you can run out of memory pretty quick. Then you can get messy. So the terminal case, in this case, it's that. And also, you know, when you are calling that function within its body, you are reducing the problem to a smaller problem. So if we're all good, let's move on to higher order function. As I said, in Haskell, you can have functions that have functions as parameter. So far we've been seeing like a function declaration with just like types. But in Haskell, you can have functions that take other functions as parameter and even return functions. Those are called higher order function. And under this notion of higher order function, we will talk about like Carriage Function, which is basically the idea that you have a function that takes a given number of parameters. If we look down here, we have the max function that takes 2 parameters. In this case, 2 could be to integer or to int. And it figures out which one is the greatest, I mean. And something really interesting in Haskell is if I call this function here with just 1 parameter, I will get back another function. And to demonstrate this, we can go back here. Go to my GHCI. Make sure I clear my console. Okay, so if I have my function max and I pass it 4 and 5, I get 5. Why? Because my max function, if we look at the type of my max function, we get that my max function takes 3 parameters. You know, it takes an A, and return an A. You know, the last parameter being the type the function returns. And we have this strange thing here, odd, which simply mean like A is constrained by the odd class, meaning that the type A that max accepts knows how to order himself. That's all it means. So we'll come back to that. So the most interesting thing here is that if we now try to figure out the type of max, passing it 1 parameter, we get something really interesting here. We see that we now have a function that takes only 1 parameter and return another parameter. So we started with a function that takes 2 parameters and return 1 parameter. But when we try to figure out like the type of that function, passing it 1 parameter, now we get something that takes 1 parameter and return another parameter. So what we could do, I could do my new max, equal max 4. So I'm assigning this function called max4 to a new variable, which is my new max. So when I do that, if I try to figure out the type of my new max, again, it tells me that my new max is a function that takes 1 parameter and return the max. So if you keep in mind that we already call the max function with the first parameter, which is 4, and we assign it to my new max. So now my new max takes 1 parameter and return the, you know, the greatest. That will be, so if we do my new max with and we give it 10, in this case, 10 is greater than 4, so we get 10. If instead we do 2, you know, we get our old 4 back. So this is this notion is called carriage function, meaning that you can have a function that takes several parameters, but as you are typing your code, you know, you can be giving them like partial parameters and be using them around in your code as values and only give it the last parameter when you need it. So this is very useful concept. Are there any questions on this one? I would say no. So let's keep on and now talked about like some higher order functions and advanced functions on list. And the first one we're going to talk about is map. You know, map is a higher order function. Why? Because it takes a function as parameter and it returns another function. So if you look at this definition, this declaration here of map, you see that we have a new syntax here where we have parameters, but we put them in parentheses. So when you see this, it means this is a function that we are passing as a parameter. It's a function that takes a parameter A and return a parameter B. So And then what it will do, it will, return another function that takes a list of A's and return a list of B. But the other way we can read this is we have a function, we have map as a function that takes, a function as its first parameter, a function that transforms A's in B's, and then it takes, you pass it another parameter, which is a list of A. So this function here is applied to all the A's in here, and you get the B's in there. So each A in this list will be applied to this function that knows how to get A's and transform it in B's, and then you will get a list there. So in order to, here is the definition of a map function. So again, here we are using recursion that we just talked about. And we say in here that if you give me an empty list, it being the second argument to my map function, if you give me an empty list, this underscore here means I really don't care about whatever parameter, first parameter you will give me at this point, because I won't use it on anything. So I put underscore there, meaning I don't care about it. I will just return you an empty list because there is nothing to transform here. But if you gave me a function, it being a function that takes A's and return B's, and you give me a list that takes, that contains at least one element and the rest of its element, what I'm going to do is I'm going to return a list of B's, but in this case, how do I get to those B's? I'm going to call F and pass it the X, so I'm going to get a B here, and then I'm going to build up my list. So I'm going to recall map with my function F, and then the rest of the element of the list. So again, we have a terminal case here, and then we have a recursive call here, building up our list. And so in order to try that, so let's say we have a function. So if I come back here, and we have a function that multiply by 2. So it takes an integer and it returns an integer. So its definition would simply be, I take an X and I multiply that X by, I do 2 times that X. So if we load this up, it being in the file, if we go back here to our, let me fix this. So if we reload our file, so now we have access to multiply by 2, multiply, okay, where is it? Let's see, multiply by 2. It's getting messy there. Sure, clear out a little bit. Okay, I'm gonna load instead of reloading my main. Okay, so I type multiply by 2. So if I give it 3, I'm expecting 6, so it's fine. So now what can I do? So if I have a list, let's say I have a list of things that I want to multiply, each element in the list by 2. What I do is I just call my map function. My map function being what we call a higher order function. And then I will pass my function multiplied by 2 as its first parameter. So multiply by 2. And then I will, as a second parameter, I will give it a list of elements that I want to work on. So I can have 1, 2, 3, 4, 5. So with that, I get, each element in here multiplied by 2. We get 2, 4, 6, 8, 10. So that's what we call a higher order function, a function that takes as a parameter another function and return, another function. If we look at this as a function, but we can also read it this way, that it's a function that takes a function as a parameter, a list of things, and transform that list of things using this function. Any questions here?
Yeah, I have a question, Malfo. So is it, I mean, I know this is for demonstration, but is it necessary to use the map function? Couldn't you just use the multiply by 2 and pass it a list and get the same answer?
Well, here the thing is the multiply by 2, by its definition, it takes only one type, one element, right? Like here, it takes an integer and multiplies by 2.
Okay.
But the map becomes useful when you have a collection of things, and you want to apply, a function to each element in the collection.
Okay.
Yes, so that's when your map becomes useful.
Okay.
Does that make sense?
It does make sense. And then this is another question. Do you know if there's a like a website out there, like a practice website where like we can play around with these concepts a little bit more? Like for Haskell. Have you seen anything like that?
I mean, yeah, we do have some platforms, but I think again, to me, they seem a little bit advanced. And I'm hoping that we'll be talking about all these things when we fully launch, the meetup. And we've been working really hard to, suggest something to the group while we are completing our Bluetooth training, just to make sure that we are following like the program, like kind of meeting like every 2 weeks and going through this concept, like picking up a book and working on it like chapter by chapters, while we wrap up, the Bluetooth and we come up with the final curriculum.
Okay.
Yeah, but yeah, we can take this conversation offline for later.
Okay.
Yeah. So very quick, we have another higher order function, filter. In this case, again, it takes a function, functions that take a variable of type A and return a Boolean. So this is called predicates function. It takes a list of A's and return a list of A's. So the filter, what it does is it applies this function here, it being its first parameter, to this list of A's. And when an A meets this condition, whatever condition is implemented in here, it is kept and, in the final list. So filter really does what it sounds like, filtering a collection of things based on some conditions. So if we go back here as an example, we do check if check if what can I say? Check if divisible by 2. That takes an int and return a boolean. In this case, check if divisible by 2 takes as a parameter an x, and it will return. What it will do is mod stands for modulo. So modulo is a function that takes 2 parameters. It takes its first parameter and its second parameter. And what it does is, if the rest of the division of the first parameter by the second parameter is 0, in this case, it means that that first parameter is divisible by the second parameter. So we have this function, check if divisible by 2, that will take in integers and return either true or false. True or false being the possible values of the type bool. And we can now use this function in our higher order function filter. So if I reload there and I call check if, I can get that right, check if divisible by 2. If I put 2, that's true. If I call it with 3, I'm expecting false. 3 is not divisible by 2. That's great. But now what I can do is I can call filter, and if we look at the definition we have here, filter takes in as first parameter a function that takes something and returns a bool. So we're going to pass check if divisible by 2 as that function, and then it takes a list of things. So we're going to do that. So we're going to give it 1, 2, 3, 4, 5, 6. So what we expect here is 2 will be divisible by 2. So we'll get 2, 4, and 6. So, and that's what we get. So it's literally taking this function, applying it to every single element in this list. And those that meet the condition are being retained. And those that don't meet the condition specified by this function, this predicate, are being discarded. Does that make sense?
I think it does as you're going through it, but I think practicing and applying it and really kind of getting a better feel for it is going to be helpful.
Yeah, absolutely. So, and here is another example where we get filter, we pass it a function that, compares something to 3. So this expression here is a function that takes 2 parameters, and writing this superior to 3, the 3 will create a function that is waiting for 1 parameter to determine. And once you give it that parameter, it will determine whether that thing or parameter is superior to 3. So in this case, it will run through this list, get 1, and is 1 superior to 3, it will discard 1. 5 will be retained. 3 is not strictly superior to 3, so we'll discard that, and so on. So now another higher order function. This one is a pretty big one. It's fold. The concept of folding is really about having, you are given like a collection of things, and you want to come up with some sort of summary on that collection of things. And the word summary is really vague here, intentionally vague, because summary could mean a lot of things. You know, if you get a list of things and you're trying to figure out the sum of all the elements in the list, that's like a summary of the list or the collection of things. Another example here could be you get a list and you are trying to figure out like the maximum value in that list. You know, you are kind of reducing that list to one element, which is the summary of the list. So fold is a generalization of that concept. And again, you know, it's a higher order function that takes as its first parameter a function. It takes something called an accumulator, and then it takes a list of things and return the summary. And in order to see this in action, I think it would be good to just run one example, and we will come back to this later. So again, fold takes as a parameter a function, so that makes it a higher order function, and it returns what we could see as another function. If we have parentheses around this, we could see that as another function, but we could also see fold as taking a function as its first parameter, a B parameter, an A parameter, a list of A's as its third parameter, and returning B. So those two are way of looking at fold valid in those two ways are valid in Haskell. So what is fold used for? You know, I mentioned the sum of things that we could use fold to figure out. Like if we have, let me go back to my file here. Let's say we want to write a sum function that takes a list of int, and you know, return an int. So here what we're really doing, we are coming up with a summary, which is the sum of all the elements in the list. So in that case, sum prime, I'm not sure if it's called that way, will take in a list of ints that I'm calling xs. And what it will do is here we will call the fold. We'll call the fold. And there are two functions, fold left and fold right. We won't get into that for now, but we'll come back to it at some point. So I will call this step, you know, step being a function. If we look over here, that we are passing to fold, that has this signature, this type. Okay. So, and then we will give it like the, you know, initial value that we will use to accumulate like the sum. So 0 being a neutral value for sum, and then we will give it like the we will pass it the list of the elements that we want to sum. So now we have a thing called step here that we haven't defined, and this is a good case to use Lambda expressions. So step is going to be a function that takes two parameters. So I'm calling the first parameter my accumulator, and I'm calling the second parameter x, and it will return x plus my accumulator. So for what it does, this function here, you know, does one step in the solution. So we have a list of things that we want to sum up, and we are telling him that, you know, at each step you're gonna get the previous accumulator that you had. The first case being 0, the initial accumulator being 0. And then you're gonna get one element from the collection. And then you're going to sum that element to the current accumulator. So what it will do is it will do that first iteration, grab the first element in the list, do sum that element with 0, 0 being the first value for our accumulator. And then in the next step, the new accumulator will be this value here. So that will become the new accumulator. And then it will take that new accumulator and add it again to the next X and so on. So at the end, you will get the sum of all elements in the list. So if we run this, so let me clear up this. So if I reload and I do sum prime, and I call it with an empty list, I get 0. So if I call it with 1 and 2, I should expect 3, which is the case. So fold is another way of looking at fold is really a way to help you, not worry too much about like recursive functions. Because if you remember when we did our calculate sum here, we were building the recursive call by hand. But fold functions generalize that concept. So you just use fold and you focus on the one-step function. One step meaning that you grab one value from the list and you grab whatever thing you are using to collect your summary of the list, in this case the accumulator, and you work with them to get a new accumulator, and you do that several times until you get to the end of the list, which is specified here. That's our terminal case. And looking at the definition of fold, you can see how it's a function that it's calling itself. So again, it's a recursive function. Are there any questions here?
Just going to say it's definitely getting a little bit more complex about how to construct these. I think for me, I'll probably just go back through the explanations and play around with it.
Okay. So did I hear a question there?
Not a question. Just saying that I side with Sydney. Maybe I'll have to go back through again and then I'll get it, because it's like very complicating right now.
Okay. Well, let's move on. We will get to, I think, exercises, and we will make sure that we explain this concept in a more detailed way. So the next notion, and I think this one is a little bit softer, I hope. We have, so far we've been working with types that come with Haskell, basic types. We talked about like chars. We talked about Boolean. We talked about integers. We talked about strings and list of, a collection of things. And in Haskell, you can actually define your own data type. and the syntax is this. So we did talk about bool, and we talked about it as something that can have two values, either false or true. So in Haskell, when you want to define a new data type, you use the keyword data, and you specify the type here, in this case, bool, and on the other side of the equal sign, you have the values or the different values that that type can hold or take. So this one is a built-in data type, and in order to get more information about it, so we can go in the repo and use this command info and type bool. So it's telling us what it looks like. You know, it's data. Ignore this for now. We won't get into that. But here you have data bool equal either false or true, and it tells you in which files it's defined, and it has some instances here that we'll come back to, you know, later when we talk more about like type classes. But the general syntax in Haskell to define a data type is to use the keyword data and specify the type, and then specify the values. So these are called sum types because you have that bar in the middle, meaning it could be either this or that. And they're also called sum types because, you know, you can either have one or the other as value. And if we look down here at this example where we define a new data type called person, you know, we then specify on the right side how we can construct a person. So we can construct a person by giving it, you know, a first attribute, which is string, second one, which is a string, another one, which is an int, and a float, and a string. And then this is how we can create a person from this data type. So we get that syntax down there where we, you know, we are calling this person, and this person here is actually a function, this one here. We're calling it there, we are giving it, passing it like a string, a list of characters, which is matching that. And then we are passing it a second string, which corresponds to that parameter, and then an int, which corresponds to that, and a float value that corresponds to that, a string that corresponds to that. This here, deriving show, is just a Haskell syntax to help us print this person, for example, in the repo. So we can try this.
So Malfoy, after the equal sign, can you explain to me what that person, like what does that do, that person?
Yeah, so this is, so first of all, before the equal sign, so to create a data type, so we type the data keyword, and, you know, we give it a type name. So this is what you would use in your function. Let's say you are writing a function and you want to specify that that function takes a person in as a parameter. So let's say we are, my age function that takes person as a parameter. So this person would correspond to that, right? So that's like the type that you are defining here. You're giving the type a name. Okay. So after the equal sign, you are specifying how you construct values of this type. So this person here is actually different from this one, as this one here is specifying the type. So I could put something else here, they don't have to match at all. And on this other side, I'm specifying the constructor. So saying that, in order to build a person, this is a function. This guy here is actually a function that takes strings, those strings as parameter, and int, and a float, and a string. Does that make sense?
That makes sense, yeah.
Yeah. So with something like this, we could go back to our record. 1 second here. Let me clear up. So we could go back to our repo and reload everything, and we could get some information using the info command about like the person type, that the type we just created, and we get there that we get the same syntax that we wrote, and then we can actually create values of type person. So I could do that, do something like, what can I do here? Could do monthly equal. And remember, I said this guy here will be used as a constructor for, any value of type person. So in this case, I will type person, and I will give it a string as its first parameter. Let's suppose it's the full name. We'll do Manfo Felicien. The second one, we could assume it's his city. I will do Douala. The third parameter, it being an int, maybe let's say when I was born, and the year I was born, and then the next parameter is float. I don't know what that would be, but I would put a 3.4 there. Maybe it's a grade that I got in math or something. And then the last parameter is a string, let's say is the subject, mathematics. So at that point, couldn't match expected type int with actual type char. So it's complaining here that instead of providing an int, which is this, I provided a list of characters, which is right. So I will use my direction keys to the upper one to go back to the last thing I typed and fix this. So an int doesn't have double quote. So it's complaining again. Couldn't match expected type float with actual type. Yeah. So I did the same thing for this guy here. So let me just make sure that. So if I go back up, and then go back here, clear that. 3.4, and it should work now. So I just defined Manfo, so I could print Manfo just by typing it like that. And you see Manfo is a person that has that name and those characteristics. So that's how you build your types. But this is really not the best way to go with types, because here we are building a person, and supposedly this is his name, that is whatever, and so it's not really it doesn't give you the information here on what all this string and int actually represent. So a better way to defining data type is using something called the record syntax, which is here. So let me just paste this.
So it's basically doing the same thing. It's just in this syntax, so that so it's more human, so you understand what how to what data is in that data type.
Exactly, and what represents what. So if I come here, I will have to comment this, and by the way, in Haskell, that's how you comment things. So the best way to do this would be actually giving names to, let me format that and make sure that it's readable. Yeah, so again, we come back here, data, we can call this individual, make sure that we have no confusion here. Again, this type does not have to match that constructor here, or that function. So again, here we are defining person, which is pretty much equivalent to what we did up here. But in this case, we are making sure that we give name to those strings. This is the full name, that's the place of birth, that's the year of birth, that's the height, and that's the phone number. So again, driving show just means that we are using some Haskell functionalities in such a way that it will figure out how to print or how to show an individual once we create it. So this is called record syntax. And the good thing about this is once you do this, if we go back here, let me just clear my REPL. So if we reload, now we have the new data type individual in the REPL. So if I type info individual, and then I get that data type we just defined there. So it's right there. And if I try to figure out the type of this full name variable, for example, full name. So if I do type, what I get is it's a function that takes an individual as a first parameter and return a string. It returns a string. This is actually pretty cool in the sense that in other programming languages, when you define a type or a class or an object from a class or whatever it is, you have to write something that is called getters and setters, just to be able to get the values from this field, this attribute, or to set them. But in Haskell, these attribute values, they are actually functions that takes the types as parameter and return that. So place of birth would take an individual as a type and return a string, year of birth, and so on. So these are a little bit kind of advanced, but as we get used to this, it will become, easier, if I can put it this way. So again, there you see, if we try to ask the type of place of birth, it takes a person, in our case here, individual, and it returns a string. So all this means that if we construct a person with this, we can then pass that person to the function full name to get his name, pass that person to the function place of birth to get his place of birth, for example. And we'll come back to that. So are there any questions on how to define new data types in Haskell? Okay, let's move on to type classes. And we've been talking about this. We've seen them a lot. And so type classes are really a way to group types, that have some common functionalities. And in Haskell, like in many other languages, the concept of equality is something that is shared among many types. Like we have ints, integers, that would very well implement the concept of equality. For example, we have the type we just defined, like a person, that would very well welcome the concept of equality. Two people are, literally two people cannot be equal, but in the sense of them having a full name, place of birth the same, year of birth the same, the height, the same phone number. Maybe if we have two people with the same attributes that have the same values, maybe it's the same person. So we could talk about like two people being equal, or one person equal to the other. So those general concept of, that kind of run across all multiple types can be grouped into something called a type class. And a type class would actually define a set of functions that all the types that implement that type class will have those functions. So if we go to the REPL and we try to figure out the type of the equal construct, we'll get something like this. And we will get into that. So let me just open my report here. So if I get in there and I type info on equal, it's a little bit overwhelming, but what we get here is that this is a type class, and it's basically saying that any type, this little a here, meaning that any type A that wants to implement the equal type class, meaning any type A that wants to have the functionality of equal, like if you can have two instances of A and try to figure out whether they are equal or not, you will have to provide implementations for this function. So you have to tell us how to compare two instances of the type A. So you can see there that function down there, it takes one A, another A, and it returns a bool. Its possible values being like true or false. So, and down here, it tells you, all the types that actually implement this type class equal. You can see int there, which is expected, integer. You can compare two integers with the equal sign. You can compare two doubles. You can compare two char. You can compare two bools, and so on. So the way it works is you have a new data type. For example, let's say we have this data type, which is traffic light. And again, we have the syntax here, which is a sum data type, as opposed to record data type that we saw up here. That's a record data type, a record syntax, or a product. We have all those at once. But down here, we have either red, so traffic light could be either red, yellow, or green. So once we have this, what's interesting here is we could be thinking, if I have two instances of, if I define two values that have type traffic light, how can I figure out if they are equal or not? I know if I have one that is red, I have another one that is green, and then I could possibly ask myself, are they equal? So to illustrate that, if we take this very quick, I think running some example will make sense with this. Let me clear up my purple. If I go back here and I define a new data type, traffic light equal red or yellow or green. Now I go back into my repo and I reload my file so I can ask info about like traffic light. And it's there in my repo. So what I could do, I could define light 1 equal. I just put red. I could do light 2. Light 2 equal. I put yellow. So again, you see I'm using this construct here, in this being the sum type, in this being my type constructors, I can just declare a variable of type traffic light, and the way I constructed is with either red, yellow, or green. So I have that, and then I could be asking myself, is light 1 equal to light 2? Light 1, is it equal to light 2? And at that point, I get something really interesting, which says there is no instance for equal traffic light arising from the use of equal. So it's telling me that I don't know how to compare those two things because you haven't told me yet how to do so. And this is where you need type classes. Again, equal being a class. If you remember, we did type info on equal. Actually, let's do it on this operator. So as you can see, there's a type class equal that we can use to tell Haskell how to compare two instances of our light. So the way we would do it is down here, we will implement an instance of the type class equal. So how does that work? So the syntax is instance. So let's gain some time here. I can just copy this from here. And I will explain. So what's happening here is, so we're saying that we want to implement an instance of the type class equal for traffic light, for this type we just defined here. And we are telling it that, the function, this is an instance call of the function. We could put it this way. The function equal that takes two parameters, red and red, then you return true. If you take green, let's do the same thing here. And if you guys remember, yesterday we talked about infix and prefix operator in Haskell. Infix meaning that the operator, which is actually just a function, is in the middle of the two parameters, and prefix comes before the parameters. So we could do the same thing here. So what's actually happening here is we are saying that red and red are equal. That's true. Green and green are equal. That's true. Yellow and yellow are equal. That's true. And if we get anything else, combine another combination, red and green. So that's what this means. Green and red, yellow and so on. We get false. Make sure you have false there. So at this point, we have implemented an instance of equal for the traffic light. So if we have two lights, we can ask ourselves, are they equal? And the compiler will not complain. So to go back here, so now if we do light, I will reload and we'll define red light 1 equal red light 2 equal red. And if we now do red light 1 and we try to compare it to red light 2, then we should get it true. Now let's say we define another light. We do yellow light, yellow light equal yellow. Can you guys see my screen? Might be having some internet issues here.
Yes, I can see it.
Okay.
Yeah.
So I'll have to reload, load my main file. And I was about to show, if I have red light, the red light, and I have a yellow light. Oops, didn't assign a value there. Yellow. Now, if I compare those two, red light equal yellow light, I should get a false. So, and again, you know, if we compare 2 and 2, we should get through. Same for if we compare the character A with A, we should get true. And with A capital, we should get false. So what's happening here again is that, you know, the types, our type traffic light, as well as int or integer in the case of 2 compared with 2, and char, you know, in this case, A compared to A, all implement the type class equal. So once they have implementation of that type class, they know how to compare themselves. And this is the notion of type class in Haskell. So another cool thing we could do is with type class is so far we don't, the compiler doesn't know how to show the light. So for example, if I do, if I try to just, when I type 2 in and I type enter, you know, I get 2, meaning that the compiler knows how to show the 2 value that I just typed in. If I do yellow light and I do enter, and notice what we will get. We get no instance for show traffic lights. So the compiler is basically telling us, I don't know how to show traffic lights. You haven't implemented an instance of show. So that's what we will do now and teach our compiler how to show, how to show our traffic light. So if I go all the way down here and so just type it in instance show traffic light show. So show is a function. So I will take red as a parameter. So I'm doing pattern matching here because I know that my traffic light could be red, could be green, and it could be yellow. So I'm just matching the body of my function to each of those possible cases. And so if it's red, I want you to tell me it's a red light. If it's show, if it's yellow, I want you to tell me it's a yellow light. And in case it's green, show green, you just tell me it's the green light. So if we clear off this guy, or REPL, and we reload our main file, it's not happy. No scope data constructor yellow. Okay, so I did a mistake there. It's yellow. So in the definition, it's yellow. So I forgot to add the W there. So if I reload, everything seems to be okay. I'm gonna clear up. And what's gonna happen is if I define, if I do light for red. And now I try to enter light. Now the compiler knows how to show it. So in this case, red light, which is this option here. So if I define a yellow light, and then the compiler knows how to show it. So type classes are really a way to give functionalities to, like common functionalities to a set of class by grouping, like we have integers, we have chars, we have bools. They all implement an instance of the show class, so they know how to show themselves. Same for like the equal type class. And if we go back here now again and type info of let's say show. So it's a little bit overwhelming, but you see the type class show that takes a type variable. That's why it could be anything. So anything that implements this class show is put right there. And you see the function that you need to implement with a show. It takes an instance of that thing that you want to show, and it returns a string. So that's what we did here with traffic light. And, we took here, as parameters, all the possible values for traffic lights, and we return strings. And notice here that there are a lot of types here that know how to show, that have an instance of show. You see a type called word. You see a type called integer, int, char, and bool. So they all know how to show themselves. Are there any questions?
I just wanted to say, I don't know if you saw the chat, someone asked about from a little bit earlier, deriving show, what that means.
Okay, so
And then it was maybe about the print command for Haskell.
okay, so the deriving show that we have up here is actually automatically implementing an instance of show for this type. So a shortcut in Haskell is to write something like data traffic here, and then add appended deriving show. And in this case, we don't need to implement this at all. So we can just comment this out. But I think it's good to know that what you're actually writing here is producing this code automatically for you. So deriving equal, you can derive more than one class. You can derive equal as well. And in that case, and in that case, you don't need to provide this implementation. The Haskell compiler will figure out like all of this for you. Does that answer the question? I would assume yes. Are there any other question that I missed? Okay, that was from Herman. Herman, do you get the deriving show?
Yep, thanks.
Wonderful, great. Okay, so let's move on to the next notion. And see if we can wrap this up very quick before the second here. Oh, that was actually it. I think we are done with the course, the mini course, and I would suggest we take a break. I would suggest a 10 minutes break if you all agree, and come back and jump into some practical exercise that will help us, like you know, run through some of these notions.